Today, we're going to talk mostly about privacy on the blockchain, and especially privacy in the sense of not leaking your actual real-world identity. So we've talked about this a little bit before when we were talking about Bitcoin. And we said that in Bitcoin, we generally don't really save our real-world identities. Instead, we save our public keys. So in a sense, what we had there was that Bitcoin is not exactly anonymous, but it's almost anonymous. Some people call it pseudonymous or something like that. But anyway, Bitcoin identities are public keys, and they're not connected to your real-world identity. Okay. But the fact that they're not connected to your real-world identity does not mean that they cannot be connected to your real-world identity, right? So these are two different things. One is just saying that your real-world identity is not really encoded in this public key, because of course you can create as many public keys as you want. But then the other point is, can your real-world identity be leaked somehow and somehow linked to your public key? And this is sometimes called de-anonymization. So can someone find my real world identity if I use Bitcoin? And of course, I'm saying Bitcoin, but this also applies to Ethereum and all the other classical blockchains that we've seen. So at the first glance, it seems like the answer to this is no. So if you're just transacting using your laptop and you're never really going to a shop or anything, you're never disclosing your real world identity. So if your real world identity is never disclosed, and if you're only using public keys, how can anyone find out your real world identity? How can anyone possibly connect your real world identity to your public key? Now, there are two issues with this, and both of the issues come from the fact that, of course, Bitcoin and these cryptocurrencies are currencies at the end of the day. So you want to buy and sell them. So there are two questions that you have to answer. The first question is, where do you get your Bitcoins? Okay, so where do I get my Bitcoins? Or more specifically, how do I buy them? This is like the buying side of things. So how do I buy Bitcoins? And then the second question is, where do I spend my Bitcoins? And of course, this one includes conversion back to fiat currency. It also includes buying some real world items. So for the first one, imagine that you don't have any Bitcoins, or again, instead of Bitcoin, you can think of any other cryptocurrency. And let's say that you want to buy some, or you want to obtain some. There are basically two ways, right? You can either buy them or you can mine them. So you have two choices here. You can either mine or you can buy it from someone. Now, if you mine, your identity is safe, right? If I want to mine a Bitcoin, I can just use my hardware and then I can use any public key to do that. And I never have to really disclose my real world identity. So I can actually mine my own Bitcoin, and this doesn't leak any information about me because, again, remember, I can generate as many key pairs as I want. I can generate as many Bitcoin identities, public keys, accounts, whatever you want to call them, as I want. So that part is fine. The part that is actually problematic is if you want to buy it. But on the other hand, mining Bitcoin is extremely hard. We've talked about this before. You have to solve proof of work. So it's hard, it's time consuming. It's not really a practical thing to do for the general user base of Bitcoin. So even though there are miners who are actually doing this, it's not a very practical solution for everyone. So chances are that if you're using Bitcoin, you're not really mining your own Bitcoin. That's not a thing that most people do. 99.9% of people actually just buy it. But then if you buy it, you're leaking information, right? So this actually leaks your real world identity. So for example, if you use any kind of broker to buy this, or any of the famous websites that are out there where you can buy Bitcoins, you have to go through all sorts of legal procedures where you have to identify yourself. And so they will connect your real world ID to your public key, and they will know that you are the one actually owning this public key. Now, the same thing happens when you spend your Bitcoin. So let's say, simplest case, you go to a coffee shop, you want to buy a coffee, you want to pay using Bitcoins or using Ether or any other cryptocurrency. Now, what happens there? Well, when you pay a merchant, the merchant actually sees your public key, right? So when you pay, you're disclosing your public key. And why does that happen? Because, well, of course, you're creating a transaction. This transaction is taking some money from you and paying it to the merchant. The merchant usually just gives you their public key, their account, and they ask you to transfer some money to that account. And when you do that, of course, you're going to just give them the receipt, and the receipt is basically the transaction that is added on the blockchain. Now, they can choose to wait for confirmations or not, that's their business, but in any case, they're going to see the transaction, and that transaction is going to contain your public key. But now the problem is, when you pay, you're actually also disclosing your real world identity, right? So again, ideally, this should not happen, but in practice, it happens. So for example, again, imagine the case where you're just buying a coffee from a coffee shop. It's very likely that they have cameras. So it's very likely that they actually see your face. They have a record of your face. So now it's unlikely that the coffee shop actually cares about this and can actually connect these two together. But if a government requirement is there to share this information, let's say with your government, then your government can definitely do this. They can connect your public key to your real world identity. And that's a leak of information. That's basically lack of preservation for your privacy. But there are actually even better examples of this. So suppose that you buy something online. Let's say you're buying a laptop online, and you're paying using Bitcoins. Now, this is a case where you're actually voluntarily giving up your real world ID, right? Because you're buying the laptop, you're giving out your public key, and then you're also giving the merchant the address that they have to ship the laptop to. So that's a real world address. And then they can put this information together. So your public key on Bitcoin gets connected to your real world place of living. So that's another way of leaking your real world ID. Now, of course, a question that comes to mind immediately is, why should I even care? So why care? Because, well, we said before that I can create as many public keys as I like. So who cares if one of them is connected to my real world identity? Who cares if, I don't know, my coffee shop or my online shop or my government knows that I owned this particular public key? I can just create another one, right? And then I can use this new one. So for example, let's say I buy Bitcoins and this leaks my real world ID, that's fine, but it just connects my real world ID to my current public key. Now, many people think that I can just create another public key and then use that one. But if I create a new second public key, the money is in the first key. It's not in the second key. I have to transfer the money from my first account to my second account. And now all the transactions on the blockchain are public. Everyone can see not only all the transactions, but also the history of all the transactions. So if I do this, I'm not really gaining anything. I'm just transferring money from one of my public keys to another one, and basically just this transfer leaks my second public key too. So the reason I have to care is because as soon as one of my public keys is connected to my real world identity, anyone can just follow the flow of money on the blockchain, and then they can figure out all of my other public keys. So the first reason is that even if one public key is leaked, all future transactions are basically unmasked now, or maybe I have to use the word de-anonymized. So if my government or my broker or my coffee shop or whoever knows that this particular public key belongs to me, then they can just track whatever this public key does on the blockchain. And so if I've bought 10 Bitcoins and I put them in one of my public keys, in one of my accounts, I can transfer them to a new account. I can create a new account whenever I want, and I can transfer them, but everyone sees that transfer. So anyone who's following the old public key sees that the money is actually flowing from the old key to this new key, and they can very likely figure out that, okay, this new key belongs to the same person. So they can actually keep tabs of who owns each one of these public keys. But actually, I have an even bigger problem. So you see, if all of the future transactions are de-anonymized, that's one thing. But actually, even all of the past transactions are de-anonymized. Okay? So this is the second problem. So the same as above, even if one public key is leaked, all past transactions are also de-anonymized. So let's say I have an account and I'm using that account to buy a laptop online, and they figure out that this particular public key belongs to Amir. So what can they do? Well, they know the history of all the transactions because the entirety of the blockchain is public. So they can just go back and see which public keys paid this one. And again, they can just look at the flow of money, but in reverse. And they can find all the transactions that ever paid me. And of course, all the transactions that paid those, and so on. And at that point, it's just statistical analysis. They have to just figure out like which one of these public keys that are paying are actually other people paying me, and which ones are my own different avatars, basically. So it's not that hard to figure that out because the information is there. So I have a big problem here. And my problem is that if I want to really have privacy on the blockchain, I have to make sure that none of my public keys are leaked. And again, when I say leaked, I mean connected somehow to my real world identity. So I have to make sure that whenever I'm doing any kind of transaction, there is no way to trace it back to my real world identity, to my real world address, anything like that. Now, how can I do this? Well, one thing I can do for sure is to make this a little bit harder. But okay, sorry, before going there, I just want you to see how terrible this is. Like, just to get a sense of this, imagine that you're using a credit card. And normally, if you use a credit card and let's say you go to 7-Eleven, you buy something and you pay by credit card, if you're an old-timer like me and you don't use these fancy QR codes, they actually just see your name, right? So they see your name, they see your credit card number, that's all. They would have no idea what you're going to do with your credit card in the future. There is no way to connect that, right? Of course, they can keep tabs on you and they can use some information for advertising. But if you, let's say, buy something from Amazon or buy something from 7-Eleven, they can use your credit card as a way of connecting all of your purchases, but they can only see the purchases that you're making from their shop, right? There is no way for them to see the transactions that you're doing with other merchants. But this is not the case here. Here, actually, if you're using Bitcoin instead of a credit card, you're leaking all of your future transactions. So even transactions that are done with other people, so anyone can see those. And also you're leaking all of the transactions that you've done in the past. So if I want to say what this really looks like, it's as if every time that you use your credit card, you're giving the whole statement of the credit card also to the merchant, so they can see everything you've ever done with this credit card. And then you're also promising to give them all of the future statements of your credit card so that they can see whatever you do in the future. So it's really a terrible thing. Okay, how can I protect against this? And this was actually part of your homework. In the homework, we accepted all sorts of answers, even answers that don't really work in practice, as long as they made it harder to do the statistical analysis. But actually today we're going to mostly focus on how to do this correctly. So how to keep private, how to keep basically the connection between public keys and real world identities private. Of course, the first solution that comes to mind is don't leak your real world ID. But again, that's not very practical because then you have to mine your own Bitcoin and then you have to figure out how to avoid disclosing any of your real world ID whenever you're spending your Bitcoin. And that might be possible. Technically, I don't have a proof that that's impossible, but it really looks impossible. Like, if I want to buy something online, how am I going to get delivery without really showing any kind of real world ID? It might be possible. I don't really know how to do it in a reliable way. And also, if I want to just mine my own Bitcoin, I need a lot of hardware. So yeah, not that great. So the impractical solution is going to be to just keep your real world ID to yourself and basically never leak your real world ID to anyone. Okay? But I need a more practical solution. And a practical solution would be to just break the links between the two types of ID. Okay? So break the link between your public key and your real world ID. So this is what we're going to focus on today. How can I break this link? How can I make it so that even though people knew that this particular public key belongs to me, I get a new public key and I get my money into this new public key, but no one knows that this new public key belongs to me. Okay. So Here's a first idea that comes to mind, and actually this is something that a lot of you came up with in your homeworks. If I just create a ton of different public keys, and if I do a lot of transactions between them, then it becomes less likely that some sort of statistical analysis can pick up on that and figure out which ones are actually my identities and which ones are identities of merchants or friends or other people that I have paid to. So it's just be chaotic, basically. And this is what most people, most privacy conscious people actually do. And it works to some extent. It seems to be working. There's no proof that it works. It's good enough for a lot of people. So basically, the idea here is that every once in a while, create a lot of accounts. Because creating accounts is free, right? You can create as many as you want and just randomly move money in these accounts. And of course, don't keep all of your money in the same account. You randomly move the money around. Maybe if you have 5 Bitcoins, you transfer 4 Bitcoins to one account, and then from there you leave 1 Bitcoin, transfer 2 Bitcoins somewhere else, 1 other Bitcoin somewhere else, and so on. You will basically make it really hard for anyone to track what's happening. You just create, I don't know, you have 1,000 accounts, money has flown in all sorts of crazy ways throughout them, and it makes it really seem like these were the accounts of many different people who were actually paying each other. Now, this idea actually has another name, and I'm sure you've heard of this. This is called money laundering. So in this course, we've seen how to gamble. This is now about how to do money laundering. And the problem with it is that actually we have very sophisticated techniques to figure out that something like this is happening. So you can just Google something called AML, and you will find all sorts of anti-money laundering ideas and technologies and algorithms. So if you do something like this, if you're chaotic, you create a lot of accounts, you move your money in a very random and unpredictable way, it's likely that you will actually get some privacy. It's likely that your local coffee shop or your, I don't know, broker or exchange cannot really track you, but your government still can. So this one gives you privacy. And this is like a privacy with a huge asterisk. So gives you privacy with respect to, let's say, small actors. But it doesn't really give you privacy with respect to more sophisticated people or governments who can actually figure out how to follow the flow of this money. And I mean, I don't know, they have a bunch of machine learning algorithms that figure out which one of the accounts are actually yours and which ones aren't yours with very good performance. So what we actually want to do is some sort of money laundering or some sort of privacy preserving transfer of money between your accounts so that it's really impossible to connect the two accounts together. And this is where we get to the second idea for having privacy. And this second idea is to use a mixer. Now, what is a mixer? A mixer is basically a service where a lot of people put money in and they get their money back in a different account. So you can think of it like this. Let me see. Like this, okay. So let's say this is my mixer. Anyone can transfer money to the mixer. And usually the mixers have a fixed amount. So let's say this is a mixer that always takes 1 Bitcoin, or if you're on Ethereum, it takes 1 Ether. I don't really care, it takes 1 unit. So everyone sends the same amount of money in. And so let's say I'm doing this with different accounts. So maybe one person is using public key 1 to send 1 unit of money to the mixer. Another person is using public key 2, public key 3, and maybe I have thousands of these. And then let's say this person 1 has another public key, which I show as public key prime 1. And then the mixer pays them 1 unit. And similarly, person 2 has another public key, and the mixer pays them 1 unit. It's not exactly 1 unit. The mixer also takes some commission, some service fee. But the important point is that these things should not be really distinguishable, right? So if I have a situation like this, and just think of this mixer as someone, let's say this is just a person, it's like a friend, and you have 3 people paying into the mixer. Now, normally, again, we will not have just 3 people. We would have something like thousands or tens of thousands of people paying in. But everyone is paying in the same amount. So look at this from the point of view of someone who's observing the blockchain. So they just see that a ton of people are paying 1 unit each to the mixer. And then when I pay 1 unit to the mixer, I tell the mixer my new account address, and then the mixer pays me, let's say, 1 minus epsilon. And the mixer does the same thing for all of its clients. So again, from the point of view of someone who's just seeing the blockchain, they see that a lot of people are paying 1 unit each to the mixer. Those are the transactions that they're seeing. And then they're seeing that the mixer is paying the same amount of money to a bunch of new addresses. And these are new accounts. These are accounts that were never used before. Okay? So now the really nice part here is that if you're just seeing the blockchain, you cannot create any kind of conclusion about which one of the initial accounts, for example, this one, was actually corresponding to, let's say, one of the final accounts. So you can basically find out no relationship between initial accounts and final accounts. You don't know which one of these new accounts belong to which one of the depositors. Because all you're seeing is that each one of the depositors is paying 1 unit to the mixer, and then the mixer is paying 1 minus epsilon to each one of these new addresses. So as an observer on the blockchain, you know the addresses that deposited, you know the addresses that received money, you don't know which one corresponded to which one. Okay? And of course, if a lot of people use the mixer service at the same time, then it's going to give much more privacy, right? So your money is basically indistinguishable from the money of all the other people who are using the mixer service, right? And so if many people use this, then your money becomes indistinguishable from many other people's money. And also your accounts become indistinguishable. So no one can really connect any of these new addresses to the real world identities. So even if the government or some malicious actor knows that this public key 1 belonged to, let's say, Amir, no one knows that, no one knows which one of these final public keys belongs to Amir. So I got a lot of privacy out of this. Okay. What are the problems? So why would I not use a mixer? Okay. Yes, so there is actually a really nice point in the chat. can we trust the mixer to not leak the link between our two accounts? Yeah, actually, we cannot trust the mixer. And in this course, we never trust anyone. So the main problem here is that this is a centralized solution. So this is centralized, which means that, well, we have a central entity. We have the mixer, whoever is giving us this service. And of course, no one on the blockchain knows the connection between my initial account and my final account, but the mixer knows that. So what if the mixer leaks it? So I have this problem. The first problem is that the mixer knows both of my accounts. I don't like that. But there's actually an even bigger problem here. Can you spot an even bigger problem? So of course, I'm not getting the privacy that I hope to get. I'm getting privacy against everyone except for the mixer, but there's also a bigger problem. Yes, this is exactly the problem as you mentioned in the chat. The mixer can keep the money. So this is the other issue. The mixer might steal my money, and there is nothing I can do about it. Right? And especially imagine if you're living in a country where these mixing services are illegal. I don't think they're illegal in Hong Kong, but let's say you're in a country where this is illegal. So this mixer person, they're actually just a criminal according to the laws of your country. So there's no way you can go after them. They're not going to disclose their identity. So you're just giving out your money and also both of your accounts to some shady actor, and you don't know if you will ever get them back. You don't know if they will keep your secret or they will just share it maybe with your government. You don't know if they will keep your money or not. So it's very risky. So not a great idea. Now, what do we want to do to avoid this? What kind of solution can we have? Ideally, I like to be able to do several things. So first of all, the mixer might steal my money. So I want to create a mixer that is trustless. So I need these properties. The first property I need is trustlessness. I want to make sure that the mixer cannot keep my money. And then the other property that I like to have is, of course, privacy from the mixer. What does privacy from the mixer mean? It means that not even the mixer should know the connection between these two public keys. So I want to have a situation where I can use my first account to deposit to the mixer. And of course, the mixer now knows my first identity, right? Because everyone on the blockchain knows who's depositing. But then I want to be able to withdraw my money from using my second identity, using my second account. And I want to make sure that not only people on the blockchain, but also the mixer itself cannot make any kind of connection between the two. Okay. Now, for the trustlessness part, actually, I think you can easily think of some ideas that might work. One of the things that will very likely work is if we just replace our mixer with a smart contract. So if you can somehow have a smart contract that does the work of the mixer, you can be sure that it's not going to steal your money, right? Because it's a smart contract, we know exactly what it does. If you don't code it to steal, it will not steal. So maybe instead of trustlessness, I want to just say that I want to have a mixer smart contract. And if I do this, if my mixer is a smart contract, then privacy from the mixer doesn't have much meaning anymore. It's basically just privacy from everyone, because whatever is known to a smart contract is known to everyone on the blockchain. Okay. So all we get to is that we have to somehow design a mixer that works as a smart contract. Now, this is the main topic now. So let's see. I want to first tell you something about a new cryptographic system that we have not seen before, and this is what we call blind signatures. And the role of this will become apparent to you really fast. So imagine a scenario like this. Let's say you have a bank. This is a bank. And let's say that this bank has the authority to issue banknotes. Or maybe instead of banknotes, let's call them checks. So let's say you're one of the customers of this bank. You have an account with this bank. Now, again, I know that many of you are too young to have used checks, but let's say that you want to write a check and you want to pay me using a check. So how does that work? Basically, it's like creating your own banknote. So you're a customer. So let's do this. Let's say Alice is a customer of the bank. And let's say that she has an account with the bank. But only the bank knows Alice's balance. Okay. And let's say that Bob is also a customer of the bank. And now let's say Alice wants to buy something from Bob. So Alice wants to pay Bob. This is the next thing I want to do. Alice wants to pay Bob. But crucially, we don't want the bank to figure out that Alice is paying Bob. So we want security, or actually privacy is a better word. We want privacy with respect to the bank. So I cannot just tell the bank to do a transaction from my account to Bob's account, because if I do that, then the bank knows that I'm the one who's paying Bob. The bank should see two things. The bank should just see that money leaves Alice's account, and it should see that money enters Bob's account. Okay. Now you might think that if the bank can see both of these, both Bob's entry and Alice's exit of money, then it can figure out that Alice paid Bob. But that's not necessarily the case, especially if all the payments have the same size. So imagine that everyone just keeps paying each other in $5 increments. Okay. So all the bank sees is that a lot of people are losing $5 from their accounts, and a lot of people are gaining $5 in their accounts. And the bank cannot really connect these together. So the bank doesn't know if it's Alice who's paying Bob or it's someone else who withdrew 5 units. And this is very similar to how banknotes work, right? So imagine that you go to the bank, you withdraw some HKD banknotes. Let's say you withdraw some 100 HKD banknotes. So if Alice does this, and then Alice gives one of these 100 HKD banknotes to Bob, and then Bob goes back to the bank and deposits it into his account, the bank has no way of knowing that it was Alice who paid Bob. Now, of course, in the real world, our bank accounts have serial numbers. So that's not great. The bank can actually figure out that, oh, this was the bank account with this particular serial number was the banknote with this particular serial number was a banknote that I gave to Alice. And then if Bob is depositing it now, so probably Alice paid Bob. But just imagine that we have some sort of banknotes that are impossible to forge, but also don't have a serial number, or at least the bank doesn't know their serial number. So if the bank cannot track the serial number of the banknotes, all the bank sees is that Bob is depositing, let's say, these many 100 HKD banknotes, and the bank has no idea where Bob got these banknotes from. Okay. Now, of course, I want to do this in a digital setting. So how can we do it in a digital setting? And again, at this point, we are not talking about blockchain at all. We're just talking about a bank that has a bunch of customers, and these customers want to transfer money between themselves, but they want to have privacy with respect to the bank. They want to make sure that the bank doesn't know who they're paying. Okay. So let's just start with our original idea. So the idea is to issue banknotes. Right? And a banknote will basically just be a string. So I will have a string that says, I am a banknote and maybe I have a serial number. This is my serial number. And let's say I'm worth whatever, 100 HKD. Okay. If the bank issues a banknote like this and signs it, so let's say this is my banknote, so I'm going to just show this with B. So let's say this is B. So if I have B and the signature of the bank on B, and I'm assuming that the bank has already announced its public key to everyone. So I can kind of treat this like a banknote. So if I'm Alice and I have this, I can just give this to Bob. And then Bob knows that this was a banknote. It was really issued by the bank. Now, of course, we have to solve the problem of double spending. So how to avoid double spending? Because, of course, in this case, Alice can just take this banknote from the bank. Again, the banknote is just this string and the signature of the bank. And she can give this to many different people. This is just some digital file, right? So she can just copy it as many times as she likes. So if you're Bob and you receive this banknote, how can you be sure that there is no double spending? How can you be sure that you can actually deposit it into your account? And well, the answer to this is that since we have a central bank, the bank can just keep track of this for us. So the way we avoid double spending is by depositing immediately. So what this means is that whenever I receive a banknote, I immediately go to the bank and deposit it into my account. And then the bank actually keeps track of the serial numbers of all the banknotes that have been used. So let me actually just put my bank here again. So there's this bank, and the bank just has a list of the used serial numbers. And the bank makes sure that any serial number can be used only once. So basically, I don't really have banknotes now. I have single-use banknotes. I have banknotes that can be used exactly once. So Alice takes the banknote. The protocol is now like this. Whenever Alice wants to pay, Alice goes to the bank and she says, I want, let's say, these many banknotes. And let's just assume that all of our banknotes have the same value. Let's say all of our banknotes are worth 100 Hong Kong dollars. So if she wants 1,000 HKD, she just goes there and she says, I want 10 banknotes. The bank just creates 10 banknotes with different serial numbers and signs these banknotes, gives them to Alice. And then if Alice wants to use some of them to pay Bob, she just gives them to Bob. So payment is just sharing the banknotes. And as soon as she shares the banknote, because Bob cannot trust that this is not double spending, Bob goes to the bank and immediately deposits it. And if the bank does not accept the deposit, if the bank says that this serial number was used before, then Bob will not accept the payment. Bob will say, you're actually double spending. Now, we have a lot of problems here. Of course, the first problem is the problem of serial numbers. I need the serial numbers to make sure there is no double spending, right? But the serial numbers can be used to track the flow of the money. So if every one of these banknotes has a serial number, the bank can just know that, oh, I gave the banknote with this particular serial number to Alice. And if Bob is depositing it now, that means that Alice paid Bob, okay? Which defeats the whole purpose of wanting to have privacy from the bank. And we actually have another problem here. Can you see another security issue? So whenever we have a centralized system, it's usually that the central entity who has control over the system can do all sorts of malicious things. What can the bank do here? The bank can actually issue different banknotes with the same serial number, right? So if different people are taking their money out, the bank can just give them different banknotes, but the bank can just reuse the serial number. And then even if one of them deposits the money back, then the bank will not pay the others. Right, okay. So we have really two problems now. We have the privacy problem, and we have this extra problem that the bank has control over the serial numbers. How can we solve this? Well, it seems in an ideal world, if the bank did not know the serial numbers, then we would not have a problem. So my solution is that the bank must not see the serial numbers. Now, how does this help? Let's say that Alice chooses the serial number of the banknote herself. If Alice chooses the serial number, and if that serial number is not given to the bank, then the bank doesn't know the serial number, right? And because the bank doesn't know the serial number, the bank cannot use the serial number to track the transfer. So when Bob puts this back to the bank can check the signature. The bank can make sure that this is a valid banknote. But since Alice chose the serial number and the bank did not know the serial number, the bank cannot know that this was Alice's banknote. Okay. So we're getting somewhere, but it's still not working. Now, the problem with this is that I actually need the signature of the bank on my banknote, and the banknote contains the serial number. So I somehow have to get my bank to sign this without actually seeing it. So I need the bank's signature on B, but I have to make sure that the bank does not see B because B contains the serial number. But if I can somehow magically do this, then I have the extra benefit of being sure that the serial numbers are unique with very high probability, right? So I can say that I want my serial number to be, I don't know, 256 bits or 1024 bits. And if Alice chooses that serial number uniformly at random, then it's very unlikely that someone else chooses the same serial number as Alice. So we will also not have this problem of clash of serial numbers, and we will be sure that the bank has to actually pay for every banknote that was issued. Okay, but how do you make it so that the bank does not see the serial numbers? So the bank has to sign something. The bank has to sign the string B without actually seeing B. Okay. And this is the main topic of today, which is blind signatures. We call it a blind signature because the person who's signing doesn't know what it is that they're signing. Now, this might sound ridiculous, like how can you sign something without knowing what it is, especially in a digital sense? Of course, in the real world, I can have a situation where I just cover your eyes and you sign something, and then you don't know what it was that you signed. But how can I cover someone's eye digitally? I mean, in a situation like this, when they're just signing something using a digital signature. And actually, let's say that we're using RSA signatures. So let's say I want to have RSA blind signatures. Here's the trick. So in step 1, Alice creates the banknotes. And let's call this banknote B. And remember that the banknote contains the serial number. And remember that we also assume that all of the banknotes are worth 100 Hong Kong dollars. So this bank knows that it's never issuing banknotes of any other value. All the banknotes are always 100 Hong Kong dollars. And so Alice really gets to only choose the serial number. If she changes any other part of this, then she will just have an invalid banknote. Okay, so she creates a banknote B, and now we want the signature of the bank on B. Or to be more specific, we want the signature of the bank on the hash of B. So let's say that my second step is that Alice hashes B and obtains H. Okay. And all of this is assuming that the bank has announced its public keys. And we're using RSA. Actually, yeah, it's going to have just one public key, sorry. The bank has announced, well, we used to call this E, remember? So the bank has announced E, and it has also announced the modulus N that we used for the RSA. And the bank also knows a secret key, right? So it has announced E and N, but not the secret key D. So the bank knows D, everyone else knows E and N. And remember, E was what we used for encryption and also for verifying signatures. D was what we used for decryption and also for signing. So the bank is the only one who can sign, so only the bank knows D. But E and N are the public key. Everyone knows how to verify a signature, and everyone knows the modulus that they have to use. So now Alice has created a banknote. Alice has hashed it and obtained H. What is her goal? She wants the bank's signature on H. So Alice wants to obtain the bank's signature on H. But what is the bank's signature on H? We're talking about RSA, so remember it's just H to the power of D. So she just wants to obtain h to the power of t. And again, remember that all the calculations are modulo n. But at the same time, she does not want to disclose either B or H to the bank. We don't even want to leak the hash to the bank, because when we later pay Bob, Bob is going to give back this signature to the bank, and we don't want the bank to be able to track it back to Alice. So Alice wants to obtain H to the power of D, but she doesn't want the bank to see H, okay? So, but the bank should have no information about H. Should have no info on H. This is our goal. Okay, so here's the next step. Let's say that I just take H and I multiply it by something, right? So let's say Alice computes H prime, which is just H times R. And let's say R is just a random number. Alice chooses a random number, multiplies that into H, and calls that H prime, where R is a random number. And again, of course, modulo n. And then let's say that Alice sends this H prime to the bank to sign. And let's say that the bank just signs whatever garbage we give it. The bank doesn't care that the string that we're giving it doesn't look like a banknote or the hash of a banknote or whatever. The bank just deducts 100 Hong Kong dollars from Alice's account and signs it. Okay, so step 4, Alice sends H prime to the bank. And step 5 is that the bank signs H prime and sends the signature back to Alice. Now, what is the signature? The signature is basically H prime to the power of D, because that's how you sign, because we're using RSA. So now Alice has H prime to the power of D, but remember she wanted H to the power of D. So H prime to the power of D is not that great. So in this step, in step 6, Alice has H prime to the power of D. But what is H prime to the power of D? H prime to the power of D is just H to the power of D times R to the power of D. So if only Alice could get rid of this R to the power of D factor, she would be happy, right? Then, because remember, Alice wants the signature on H, which is H to the power of D. But what she's getting here is not really H to the power of D. She's getting that multiplied by R to the power of D. So we want to somehow get rid of this part. But the problem is that as Alice, we don't know D, because D is the private key of the bank. So I don't like the fact that I'm getting R to the power of D here. What can I do? What can I do to make sure I don't get R to the power of D? Well, I can use the RSA property. What was the main RSA property that we had with these numbers, with the E and D? Yes, the thing in the chat is absolutely correct. So our RSA property was that if I take some number, let's say if I take any random number R, and I raise it to the power of E times D, I get R back. right? Why was this? Because this is basically saying I take R, I first encrypt it, and then I decrypt it. So if I encrypt and then I decrypt, of course, I want to get the same message back. Now, I want to use this property somehow. So here, instead of saying that H prime is H to the power of R, I'm Alice, so I know E. Remember, E is public. So instead of H times R, I do H times R to the power of E. Okay, because I can do that. R is just a random number that I chose, H was a hash that I knew, and E was public knowledge. So I define my H prime like this. And if I define my H prime like this, now let's see what happens when the bank signs it. So the bank signs H prime and returns H prime to the power of D to Alice. Now Alice has H prime to the power of D, but H prime was H times R to the power of E. So H prime to the power of D is just H to the power of D times R to the power of ED. Okay? But again, R to the power of ED was R. So this is just H to the power of D times R. But Alice knows R. And since Alice knows R, she can just divide by R. So now in this step, let me just use another color. Alice computes H to the power of D, which is just H prime to the power of D, which was given to her by the bank, divided by R. And I'm saying divided by R, but actually what I mean here is multiplied by the modular multiplicative inverse of R, right? And again, this is mod n. So now Alice found a signature on H, because this is H to the power of D and she could actually compute it. So you see, the bank actually signed H without ever seeing it. What did the bank see? The bank only saw H prime. And H prime was not H. H prime was H multiplied by some random garbage that Alice created. So the bank doesn't know what it was that it signed. The bank just knows that it signed one banknote. And of course, when the bank signs this, it also deducts, let's say, 100 Hong Kong dollars from Alice's account. Okay, so the bank just charges 100 Hong Kong dollars whenever it wants to give you a signature, and it doesn't care what it is that you're giving to it, it just signs it. 100 Hong Kong dollars to sign anything. So as Alice, you give the bank this particular H prime, which was crafted like this. So you take some value of R, some random value of R, raise it to the power of E, multiply it by the thing that you actually want the bank to sign by H. And then when the bank signs that, you just take the signature, you divide the signature by R, you get a signature on the hash that you desired. So the bank doesn't know what it signed, but you got the signature that you wanted. Okay. Now, how does this continue? Well, if we just want to go on with this in step 7, Alice sends this banknote. So let's say B, and now H to the power of D to Bob. So remember, this is the original banknote that also has a serial number in it, but the serial number was just a large random number that was chosen by Alice. And this is a signature of the bank on the hash of this banknote. Now, the bank has never seen this signature before, but it's a valid signature of the bank. So anyone can verify that this is really a valid signature of the bank. Okay. So Alice sends this to Bob. And then, as usual, Bob immediately deposits it, because that's how we make sure there is no double spending. So Bob immediately deposits it with the bank. So Bob immediately sends B and H to the D to the bank. Now the bank can actually verify its own signature, right? So the bank can take the hash of the banknote, that's H, and it can verify that this is actually a valid signature. So the bank verifies the signature. Verifies its own signature. And now if the signature check passes, the bank has to do two things, right? So it's increases Bob's balance by 100 Hong Kong dollars. And it also adds the serial number of B. Oh, sorry, this was small b. To the list of spent coins, or to the list of spent banknotes. Okay, so this ensures that no one can use the same banknote ever again. Yeah, so this is our very weird situation. So again, remember, Alice creates B, its hash, and also some random number. And then Alice actually sends H prime, which is H times R to the power of E to the bank. The bank sends back its signature on H prime, which was H prime to the power of D. And then if we have Bob here, Alice sends the banknote and H to the power of D to Bob, because after receiving H prime to the power of D, Alice could actually compute H to the power of D, which was the signature on this hash. Bob sends this to the bank, B and H to the power of D. The bank verifies this, and then it just adds B to the list of used banknotes so that no one else can use the same banknote. But the really crucial point here is that if you imagine that thousands or tens of thousands of people are doing these kinds of transactions at the same time, the bank sees a banknote, it can verify that this was a banknote that was actually signed by this bank, but there is no way for it to say which banknote this was. So if I have 1,000 different Alices and each one of them is taking out one banknote and paying to 1,000 different Bobs, then the bank cannot connect which Alice paid which Bob. And that's, of course, the privacy that we wanted here. So in other words, the deposits and the withdrawals are not really linked together. So that's nice. But this was just a huge detour into the world of blind signatures. Let's go back to our main topic. And our main topic was how to have a mixer. So I want to have a mixer like this. I want to have it as a smart contract because I want it to be trustless. And I want to also have privacy from the mixer. So the idea here is that I have a bunch of Alices who are putting money into the mixer, and I have a bunch of Bobs who are taking money out of the mixer. But I don't want the mixer to be able to connect these identities together. Okay? So I'm going to have a mixer, which is a smart contract now. So Let's put it here. And I'm going to call this one Mixer Smart Contract. Now I have a problem, and the problem is that I need someone to actually sign for me, right? So let's say I have a situation like this. I want to basically use my contract to replace the bank, but I can't really do that because here's the thing. I have Alice, and let's say that Alice is paying 1 Ether in here. What else is Alice doing? Alice is also giving this value of H prime, okay? But this H prime, it actually depended on some RSA keeper, right? So the idea here was that I have a bank, and this bank has a private key D and a public key E. And of course, we've seen before in the lecture on RSA that E and D are connected to each other in a very specific way. And the most important point there was that D is private, right? So only the bank knows D. But this means I cannot just replace my bank with a smart contract because nothing in a smart contract is private. Anything that you have inside the smart contract is known to anyone who's following the blockchain. So I just can't have the concept of a D like this. I cannot have a private key that belongs to a smart contract. But I need that because that's actually how I get my signatures, right? So the smart contract can know E and N, but there is no way I can save D in the smart contract. So I actually need someone, some external actor, to take the role of the bank. And the role of the bank was to just give signatures. So now I'm going to have this Mixer smart contract, and I'm going to also have a bank. And this bank is just some real world person. I'm calling it a bank. It's not really a bank, but whatever. It's going to take the role of the bank. And the way this works is that at first, my bank is going to generate RSA keys. So the bank is going to generate a modulus n, which remember was the multiplication of 2 prime numbers, if you remember the lecture from RSA. It's going to generate some number E, which is the public key, and it's going to generate some number D, which is the private key. And then the bank is going to tell the mixer, here's N and here's E. And the mixer smart contract is going to save the values of N and E. Now, after this happens, Alice can give 1 Ether to the mixer, and she can also give the value of H prime to the mixer. So H prime will be saved in the mixer, in the contract. And remember, again, H prime was H times R to the power of E. Okay, now, the only person who can sign H prime is the bank. So the mixer, the smart contract here, just gives some time to the bank to sign it. Actually, let me put some numbers here. So this is the first transaction. This is the second transaction. And now the bank has some time to give the signature. So it has some time to give H prime to the power of D to the mixer. Now, what happens if the bank doesn't give the signature to the mixer? Well, we can just code our mixer. So our mixer is a smart contract. We can code it so that it refunds Alice. So whenever Alice pays 1 Ether, this money doesn't actually go to the bank. It goes to the smart contract. And the value of H prime also goes to the smart contract. And then the bank has to give a signature. If the bank doesn't give a signature to the smart contract after a while, then Alice can just get her money back from the contract. And the really important point is that the bank cannot just give you fake signatures, because N and E are public. N and E are known to the contract. So when the bank gives H prime to the power of D to the contract can verify the signature. The contract can take this H prime to the power of D that was given by the bank and raise it to the power of E and check if it was the H prime given to Alice. So the contract can check the signature because, again, checking the signature only needs the public key. Okay, so this is the third step. And then we will, of course, have a ton of people doing this. Maybe I have, I don't know, 10,000 different Alices who are just giving money to this contract. And then after a while, let's say after 2 days, the contract goes into the phase where people can actually get money out of the contract. So in this phase, I will have Bob, and Bob has received basically this, the banknote and the signature on it from Alice. Now, in this case, since I want to use it as a mixer, Bob is actually Alice. So Bob is just another account of Alice, right? But there is no way to know it on the blockchain. On the blockchain, they have different public keys. They're different accounts. So even though Bob and Alice are now the same person, there is no way to know that. So Bob is just going to give the banknote and the signature on it, H to the power of D, to the mixer. And now again, the mixer can do the job of the bank. It can verify that the signature is correct, because here's the thing. Again, the mixer could not create a signature because it's a smart contract. It cannot have a private key saved in it because then it would not be private, but it can always verify signatures. So I only needed the bank here to give me the signature. But here, when Bob sends some message like this to the smart contract can actually verify that this is the correct signature, and then the smart contract can give the money back to Bob. So the smart contract gives 1 Ether to Bob. Step 5. Okay. So you see, now I have a situation where my money never goes to the central entity. I still have centralization here. I have a particular bank in there who's the person giving me these signatures. And of course, I have to make some small changes. I have to give some incentives to the bank. Maybe I have to give some small fee epsilon to the bank. And then here, Bob will not get all of the money back. He will get 1 minus epsilon. And of course, there are gas fees and all sorts of things like that. But other than those details, right now I have a situation where the bank, even though it's a centralized entity, it cannot really steal my money because the money always stays in the smart contract. And it can also not know anything about the connection between the deposits and the withdrawals, because the only thing it can see is that a bunch of people deposited, I gave signatures for all of them, and then a bunch of people withdrew. Okay. We can actually make this even more decentralized. We can say that instead of one bank, we can have in the same contract as many banks as we want. And then basically, whenever Alice is depositing, she has to say which bank she's depositing with. So she has to say, I want signatures from bank number I. And then when Bob is withdrawing, he has to say, here's a banknote and here's a signature from this particular bank. So I don't even need to have just one bank. I can have as many banks as I want in my mixer smart contract. I have just one mixer smart contract, but I can have many banks. Now, of course, then the property that I have is that the deposits and withdrawals to each bank are going to be indistinguishable from each other. So if 10,000 people use this mixer smart contract and they use the same bank for their signatures, then no one on the blockchain, including the bank itself, can tell which deposit was connected to which withdrawal. Okay. So we are out of time. You can leave now, but I just have one more small point here. Can anyone see an attack here? There is just one remaining attack. What can go wrong here? It seems like everything is trustless, everything is decentralized, everything is private, but there is actually one thing that can go wrong. And the thing that can go wrong is that the bank can issue extra banknotes, right? So let's say I'm the bank, and let's say that 1,000 people have deposited money here and asked for my signature. And I've given my signature to all of them. But then I've also created some fake signatures on some fake banknotes that I created myself. And these are banknotes that didn't deposit anything in the smart contract. But of course, as the bank, I know the private key, I can sign them. So I will have valid banknotes and signatures in this step. So as the bank, I can take the role of Bob and I can take money out of the mixer. I can still basically steal money from the mixer. So we need to have one extra step and a few extra steps. The few extra steps is that the bank has to, first of all, give a deposit to the mixer. And secondly, when Bob or several Bobs give these valid banknotes to the mixer doesn't pay them immediately. Instead, the mixer just counts how many valid banknotes it receives until some deadline. And if the mixer receives too many valid banknotes, so for example, if the number of deposits was, let's say 10,000, but the mixer receives 10,001 different valid signatures, that means that the bank was cheating. So the mixer will just burn the bank's deposit or maybe pay it to other people. And then instead of paying all these monies to Bob's, it will pay them back to Alice's. So it will just refund everyone. It will say that the mixing failed because the bank was dishonest and the bank issued too many signatures. Now, of course, in this case, we will penalize the bank. So in practice, the bank will have no real incentive to do something like this. It will just lose money. And so in practice, the bank will not do this and we will not really need to do the refunds and everything will work out. But you just have to be careful about this. You have to be careful that you need a deposit from the bank and you need to have something in your mixer smart contract code that actually penalizes the bank if it provides too many valid signatures. And here you have to also be careful not to pay too soon. You have to wait for all the banknotes to come in. And if you had too many banknotes, then you don't honor any of them. You just refund everything back to Alice's instead of paying to the Bobs. Okay, that's it for today. If you have any questions, please ask in the chat. Otherwise, I'll see you soon.